So good morning, good afternoon, and good evening to everybody. Thanks for joining us for the third edition of Elmarco's webinar. Today, my name is Josh Manasco. I am related to and do some business development and application development for Elmarco, and I'm joined by my colleague Katarzyna Rubiszkova, who's in our sales department. So what I want to talk about first is, if you mind to switch it. Talk about first is our presenter today is Dr. Gordon Herwig. He'll be presenting on sustainable electrospinning challenges, opportunities, and applications. He's from Empa, and they're a partner of Elmarco's. And I don't want to forget that also we have two more webinar series coming up, one near the end of February and one in March, one talking about medical applications and electrospun membranes for photocatalytic applications. So don't forget to join those as well. So I'm going to hand it over briefly to my colleague Katarzyna to talk a little bit about Elmarco.
So hello everybody, all electrospinning fans. It's really fantastic that all of you are connected now. So it's my task today to talk about Elmarco, because Elmarco is the organizer of this event. So I think it's on place that you know something about us. So Elmarco is a global leader in the market of building and selling and supplying machines for making nanofibers, simply speaking. We are more than 20 years in the market, and so far we sold 250 machines globally. We are using technology called nanospider. That's the brand name of the technology. And a little bit details about the technology is that we are using wires as a spinning electrode. So basically a solution is coming on the top of the wire, is distributed by moving carriage or spinning head, as you can see shortly in a video. And fibers are generated from the surface of the wire, are coming towards the collector, which is again the wire, and are being deposited on the moving substrate, where the substrate can be anything from non-woven textile through all kind of papers or foils. So basically we are spinning roll-to-roll production, which is coming as a base from textile industry. All our machines are working in the same technology. So this is a portfolio of a machinery they'll be distributing. On the top, you can see our lab models. The most important is that everything which is developed on a small scale models can be easy transferred to the industrial scales. So for those of you are already developing and working with our machines, it's for us is later on much easy to go and jump to the real production, which is basically the target for all developments. Briefly about the nanofiber applications. I don't want to go much into the details of everything. Last time we talked about medical application, a little bit air filtration, but today we are actually combining all the application in one big topic, and that's sustainable electrospinning, because that's coming across all application, because we are going towards the environment. We are going towards the mother nature, and we're all trying to be more environmental friendly. So yeah, it's my pleasure to give a word to Gordon, and maybe Josh will talk about him a little bit.
Yeah, so I'll just give a little bit longer introduction to about Dr. Gordon Herwig. He's did his studies in University of Warwick. His doctoral research was on 3D printable biodegradable polymers. And he joined Empa in 2019, where he leads work on coatings and electrospinning for functional textiles, controlled release, and particle filtration apps. Now, I wanted to say that this is a very important topic also in the electrospinning industry as a whole, talking about sustainable electrospinning, as we need to come up with alternative solvents, a very solvent-intensive process in general, and also polymers. So it's a very important topic for us, and I'd like to welcome Dr. Gordon Herwig.
Thank you very much for the introduction, and thank you everyone for tuning in to this talk. So again, thank you very much for tuning in. This is going to be about the sustainable electrospinning, specifically challenges, opportunities, and applications, what basically we are working on at the moment and what everyone around us is working on, and definitions and transferability onto the nanospider technology, because, I mean, it has to be stated first what exactly sustainability is before you can actually apply it. All of what I'm saying is going to be actually transferable to the nanospider. That's what we are working on specifically. Some of that is already published, some of that is currently in the process of being published. The introduction was already given. As he said, I'm already at Empa St. Gallen since 2020. I'm working in the interface between academia and industry. So that means we are working with industry to realize electrospinning applications that are until now mostly known in academia. So we're trying to transfer the whole thing onto large-scale production, specifically with our nanospider machine. I am from the department Materials Meet Life, and that's in the laboratory, specifically biomimetic membranes and textiles. We're working on all sorts of different novel smart fibers, textiles, and membranes. We're looking at applications in body monitoring, drug delivery, and tissue engineering. We are also working towards physical and numerical skin body models. So everything that we're simulating, we can also realize. I am specifically of the group Skin Mimicking Structures. The lead here is Dr. René Rossi, and formerly also my colleague Giuseppino Fortunato. He was a very great mentor, especially in terms of electrospinning. And currently we're working on particles, membranes, and composite materials for biomedical and engineering applications. And with this, I'm usually working on the nanospider. We have some modifications that we could do there, since we already have the device since 2013. So we actually can use as little as 8 milliliters for tests, which incredibly speeds up the screening process. We also have the old wheel setup, which I'm going to get into later, why it still has some use in our group. And mostly we're focusing on green, sustainable methodologies. So sustainability, why is it actually important? I mean, everyone knows it's important, but the question is, what is that going to help us with? Of course, it has been around, this term specifically, since 1987. It's been in a UN report, and it basically means that everything you're working with, everything needs to be sustainable. So that means it has it should be based on renewable food stocks, for example. It should be based, the environmental impact at the end should be non-permanent. And that means it's all about environment, health, and economy. The bad news, currently, a lot of plastics is actually still around. Recycling would be the most sustainable method, but at the moment, a lot of it is actually landing still in landfill. And if we are looking at actually what happened since 1950s, since the polymers were properly introduced in the daily life, most of it is actually still on landfills. About less than a third is still in use, and very small amounts have been recycled, and most of them actually ended up on landfill as well. And we have some incineration. So this is a very nice graphic showing what the actual problem is. Of course, there are also some opportunities. So there are more and more reports of novel plastic waste strategies. For example, these PET and PP eating biological organisms. The good news, we actually are making progress on this, especially also with the EU legislations, specifically towards packaging and packaging waste. There was one at the end of 2020. And if we're looking at what packaging actually does, it's the main contributor of newly produced plastics and the main contributor to what is actually generated as waste. And the good news is, at the moment, with all these regulations, we're actually much better in terms of what is still on landfill. So we're still at the moment at 60% that goes towards landfill. I mean, that's from 2016, so we're already a bit better since then. And the projection is that in 2030, we're actually only going to have about 20% ending up in nature. The rest is mostly recycled, and then a smaller part also incinerated. Now, here's what we actually can do with electrospinning, how we can get involved in this whole thing. As already mentioned, it can be both materials and solvents. We So there's a couple of benefits and disadvantages when we're looking at what sustainable plastics and solvents mean. So most importantly, they can be quite expensive, which is probably the most important driving force for industry, with the regulations that will certainly change, because the more expensive versions are going to be cheaper because more demand, and all the bad solvents hopefully are going to get more expensive or phased out, simply banned. Of course, there's always the matter of resource intensiveness and competing with the food industry. At the moment, that's definitely still true. There are certain reports where it says that most of the, for example, sugarcane that's built is actually not directed into food industry, but into plastics. But also this has to and will change, I'm pretty certain. Another problem is not only just for polymers, but also solvents, that they are usually more sensitive when they are green or sustainable. That means they are often more susceptible to UV, humidity, high temperature, and oxidation. And of course, for electrospinning, you have to experiment with all of these combinations. You can't just, there's just not much knowledge at the moment on what you can use and how. And of course, one very important aspect is also flammability and combustibility versus also flash and fire points. We are, of course, with Elmarco, we have to make sure that there's absolutely no risk of any flame or anything, especially because we're working with electricity. So there's always a risk of some ignition. But on small scales, and if we're looking at exactly what is needed to have a fire started, there is definitely worth considering using some more sensitive materials that are most likely going to be fine in the nanospider, and ways to even improve these safety. Of course, the advantages are definitely biocompatibility, and that also means that most of these things can be used for biomedical applications. Biodegradability, mostly also coming with more biosourced materials. They can be soluble well if you pick the right solvent, which is not always easy, but that's certainly what we have been researching about. High customizability, so you can, with chemistry, there are basically no limits to what polymers or solvents you can still create. And actually, what is interesting, when you're switching to a green solvent, sometimes you actually get better properties than you would get from the unhealthy and non-green options. And of course, you can use it both in needle and needle-less electrospinning, maybe even more so in needle-less electrospinning. So this is some sort of building block system that we are suggesting. You can choose between different solvents. You can also mix them up. Polymers, the same. You can choose them by performance. More and more, there are alternatives that are biosourced and also biocompatible, but you can mix them as you like, and also additives. More in detail, what do these words actually mean that are constantly used? Sustainability, as I said, is the impact on environment, health, and the economy, mostly from production, use, and waste viewpoint. So all of it needs to be accounted for. Benign simply means that it's health-related, environmentally friendly, no harmful effects there. Green and renewable are the terms that we like to use, which usually means it's biosolvents or biopolymers, so that means completely from nature. Sometimes it also is meant to just mean biosourced though. And I'm coming from a chemistry background, so I'm usually seeing it from green chemistry, and that basically always means sustainable chemistry. So both production and use and waste in the end. There's a lot of terms starting with bio, which makes this whole thing maybe more confusing. Biopolymers, for example, are entirely produced from biological resources. Biosourced and bio-based means that there's a part of it from biopolymers, and we can see that nicely if we are looking at a nice graphic that I've made. Bio-based is basically a relatively large group of materials. They can have, for example, if you have a copolymer or certain parts of it that are sourced from nature, then you can call them bio-based. And biopolymer then means those are the few that actually are basically 100% from nature. On the other hand, we have degradability. There we have biodegradability, as at some point it will degrade in nature. There are certain standards. For example, there are some ASTM norms saying 0.5 to 2 years degradability, but there are certainly people misusing it and saying at some point it will degrade, and that's basically all the polymers. And of course, the most important bit is here the compostables. There are also subcategories. For example, PLA is one that needs a certain temperature, but nowadays this is actually not difficult to reach with industrial composters and also thermocomposters for home use. If you want to have any more information, there's a nice reference where you can have a look. That should do for now. One important thing still to mention is biocompatible. basically you can call anything biocompatible as long as it doesn't have any negative host responses. And that means basically all the materials will be used to some extent in the human body if it's absolutely necessary. And that means they will be called a biomaterial. That's why here this nice graphic, biomaterial can be anything. So there's a little distinction that you can make, for example, mostly defluorinated, and as far as I know, also PS, polystyrene. I have not found a direct source where you can bio-base them actually. So that means they are neither bio-based nor biodegradable, but certainly biomaterials if they have to. Then we have some polymers that are nowadays routes to make them bio-based. Interestingly, also polypropylene, polyethylene, and all the other polyesters and many other things, they are still not very degradable. There are options to chemically modify them, but that is not a very common thing to see. Then we have PVA, EVOH, so everything that contains, let's say, more organic long chain polyesters with hydroxy groups. They are mostly degradable. Some of them even compostable, but maybe under special conditions. And then we have PLA and all the other special polymers. For example, there's also polyanhydrates and polyorthoesters, which I'd like to mention as specifically degradable materials, but they are still very expensive to source. But we also have the biopolymers here, of course. So chitosan, cellulose acetate, so basically any cellulose derivatives, starch components, also polycarbonates. They can be made and mostly are made bio-based and are usually also degradable. But of course, how much is bio-based and how much is compostable is still depending on what you buy there, basically. Similar problems you also have, of course, with the solvents. They fall into the same categories. But again, the problem is you never know where you get it from. So some solvents that you're using, technically even DMF, can be made bio-based, but it's highly unlikely that you're actually sourcing that from, let's say, reasonably priced suppliers. When we're looking at very specific polymers that are difficult to replace, there are still options to make this spinnable and even green spinnable. So one of the main components is PTFE. It's just simply the best alternative to use for anything that needs to last very long in nature, because it basically doesn't degrade. And also you can use it for specific filtration applications because it's nicely omniphobic. You can actually spin it via dispersion electrospinning, but that's certainly not that easy. We are currently also working on this in the NanoSpider. With needle, it's not a problem. And melt electrospinning, of course. We have alternatives there as PVDF HFP and also THV, which is basically the terp polymer out of Teflon, and this one. This one is actually soluble in DMF or also DMSO acetone. And yes, they are slightly less omniphobic, but there's always options to improve that in post-processing. We also have a very nice group of polyimides, which is mostly used as isolators in the conducting industry. And we're looking there at processing usually from reactants. So that means they are made directly where they're needed and then basically can't be removed. But there are some customized soluble polyimides available, which we've also been using. And yeah, very interesting potential there to use them. Polyesters, which is probably the main focus point of textile industry. Of course, they are incredibly difficult to dissolve because of their crystallinity. So usually you have to use fluorinated solvents. That's nowhere green and certainly not a great alternative for using a NanoSpider. But there are actually options to use PETG or PCTG or other copolyesters in green solvents. We've actually managed that recently. So this is a very nice potential to look into. Aramids, so mostly known as Kevlars, they are relatively stiff and highly crystalline polymers. Again, super difficult to dissolve. You can use sulfuric acid, which isn't the greatest to actually have, except for cleaning purposes, or from reactants. Again, there are options to go to other nylons that are actually better to use, or simply aromatic aliphatic mixtures of them. If we then go a bit even more soluble, there are even TPUs and polyamides that are made soluble in ethanol and other alcohols. So that's definitely an option. But of course, you're then losing a bit of chemical stability, and you're also making it a bit more susceptible to hydrolysis. So it's not as stable potentially. And finally, we of course have cellulose, and other alternative options. So cellulose itself is usually not spinnable either because it's insoluble in basically everything. It's usually processed using regeneration and as viscose. That might be spinnable, but it's difficult to use in the first place, and then you would have to regenerate it afterwards. Much better alternatives are cellulose and lignin derivatives, starch derivatives, chitosan, also collagen and gelatin, even though there you have to have a look more into if a non-vegan source is acceptable. So yeah, there is many different alternatives that you can actually use. Now we have to have a look at what actually sustainability means in terms of properties of solvents. There's this nice, to begin with, relatively easy to understand concept of EHS versus LCA. So we have environmental, health, and safety objections basically, and you can rank the solvents according to this. And then you can also take in life cycle assessments, which basically gives you an idea of energy and resource demand. So you basically see the standardly as green seen ethanol, methanol down here, certain acetates, esters, other ketones, and many interesting things. What I found particularly interesting is that hexane and heptane count as relatively easy to make as in terms of energy and resource demand, of course, because you can simply take them out of the oil. But of course, that's nowhere green. So we are having to focus more on what combines both the best. And what I also found interesting, you can actually find out what's best as a regeneration technique, or let's say as a waste technique, either incineration directly, or if it's worth distilling it first, if you look at these two parameters. All of this is still relatively complex, so this gives you a first idea which solvents are good to use. There are also other methods to look into it. For example, there's this nice little table, and there are more of this kind from GlaxoSmithKline and other producers who are looking at all the various different factors that can come into solvents. The problem is this is all not that relevant for electrospinning. For example, they are having problems with high boiling points, marking it as bad, which isn't not much of an issue in electrospinning. Also, more importantly, there's no flash point mentioned, so it's not the best to look at in terms of electrospinning specifically. So what is a tiny bit better is if you compare these different tables with each other. So we have, for example, Pfizer, who's been known since 2020 for other purposes, GSK and Sanofi. If you compare all of those and how they classified their solvents, you can get a better idea which is potentially useful. For example, here with acetonitrile, we have very big issues between those. So you basically need to factor in and look into it exactly what acetonitrile is good for and what isn't. So all of this gives you a better idea again, but it's still not great. And on top of that is also the limiting factor norms and regulations. So there was another nice norm at the beginning of 23 actually, about reduction of waste solvents in gases for textile and chemical industry. So all of this will only get worse, let's say, in future, or actually from another perspective, you might say it gets better because we should have the interest that our environment stays stable. So a little summary, of course, water is still the best solvent. There's nothing, the greenest solvent, there's nothing you can say against that. Of course, the main problem with that is that you often get some soluble membranes, or at least not that easy to process membranes. Of course, there's the option of reactive electrospinning, but that's quite complex and probably not easily scalable. Then there are the known green solvents that I mentioned before. The problem with them is they're often flammable and can also accelerate degradation, especially if you look at the acids. But they show okay solubility. So you can solve it and you can electrospin with it, but the window is relatively narrow at what concentration you can do that. Then there are the more sophisticated materials, for example, from BASF. They are usually quite expensive. So if you look at methyl, THF or styrene, relatively complex to implement because often their concentration is a bit of an issue there. And then we have the more natural compounds, which are quite nice. So there are different ketones, esters, ethers, and amides that you can actually use that are biosourced, often from furfural or something, which comes from fermented biomass, which basically means there's no competition with foodstuff. So that's also good. Of course, the problem is still it's slightly combustible, or depending on which one you choose, even very combustible, so not the best either. And there are also a lot of natural compounds which are very nice, but often also aromatic, and that means you're not really quite sure how this will behave in future, if there are actually any health and safety problems. The good thing is you have super high solvation potential with these. So there are some that are really going into that are very promising, but again, it's a bit questionable to use. So general complexity, as I mentioned, is concentration matters, deregulation that still comes from EU, UN, or other regulatory authorities, and unforeseen complications in the production because they might actually mess with your substrate or might be more moisture sensitive or anything. So there are a few options that you can counter that with. For example, the spinning parameters, that's what we are working on specifically. So we're playing around with temperature, moisture. Gas composition is something very interesting. So let's say you have something relatively flammable, for example, acetic acid is still to some extent flammable or combustible at least. Ethanol especially as well. One option is to simply add more moisture to the whole system. The other option is if we are simply looking at the fuel, at the fire triangle, we barely have any heat because we're constantly blowing cold air through. We're not having high concentrations of fuel because it's basically just what's evaporating. There is no proper vat there. And the most important thing that we can influence in this case is oxygen. By simply diverting some nitrogen into the chamber, we can actually decrease all this flammability problematics. So that's a very interesting way, and it doesn't need to be very high. Just a few % of nitrogen can help to rule out basically the risk of explosion or flammability, anything in there. Of course, polymer properties are very interesting as well. That depends which polymer you're choosing, often copolymers. And as I mentioned before, you have various additives, co-solvents, and concentrations you can change around with. And of course, reactive electrospinning is still an option so that you cross-link it, for example, while it spins or upon contact with air or anything in the substrate. So all very interesting options. There's also, of course, the case, as it is probably with most industries at the moment, that you can't just switch for the moment. In this case, there are still, if we're looking back at the 1970s, there has already been introduced the 3 Rs, which is reduce, reuse, and recycle. That means that you're simply working with as small amounts as you actually need to make sure there's no additional waste. There's also the option to use post-processing. So for example, plasma coating is very nice to add the fluorinated factor without actually working entirely with fluorinated polymers. There is grafting opportunities that we are working with to make something, for example, pH responsive that you can do directly with the electrospun membrane. The next option is, of course, to reduce the solvent amount. That's why I'm mentioning higher concentrations are often better because it gives you a wider window where you can work in. It also means it's more viscous, so that's a bit of a processing problem. But with most options, as I said, with the wide window, we can still make it work at medium concentrations, let's say. Adding additives and co-solvents definitely helps with that. We also have the option to simply reduce the number of production steps. In this case, it would be adding additive ingredients, for example, biomedicine, drugs, anything like this directly into the electrospin solution. That means you're having just one step to incorporate everything into one membrane and done. And that leads you basically to composites, and they are usually made with emulsion or dispersion electrospinning, which I'm going to go into a bit more detail in the next slide. Reuse, obvious. It means that you're basically recycling or making it available again, your solvent or maybe even substrates or whatever you've used to transfer it off. But it's not that easy. You can use the scrubbing technology from Elmarco, that's all good, but then you still have to get it out of the water again. So that's not the easiest way again. And polymers, you can also recycle, which is quite important. That opportunity isn't really given with solvents, of course, but generally you have the problem that once you've electrospun onto it, you have introduced some sort of impurities like solvents, or there might have been degradation over time. So it's not ideal for recycling necessarily either, especially chemical industry wise. Of course, the best option is still a dedicated waste management. Again, Elmarco can help with this to a certain extent, maybe completely, depending on what you're willing to invest in. There is, of course, scrubbing as the most important one, but also cleaning, rinsing, drying, opportunities to recover your DMF, if that's what seems to be the case, the most used solvent for most industry partners. There are also more niche applications of composting. So there are DMF degrading microbes, and technically nothing is stopping you from actually having an industrial composter with such sort of degradation mechanism to sell your membranes and substrates and whatever you have as green. And the last option is basically oxidative catalysis. That means you're sort of burning it up, or rather you're catalyzing the oxidation of it while it comes out. But that's of course not so environmentally friendly because it's still a waste of energy and resources and everything. But at least it's not damaging to the environment when it comes out. So yeah, if we're having a look at the blend electrospinning and emulsion electrospinning, blend electrospinning basically means that you're adding multiple components into one solution. This can be solids that are getting dissolved even. It can be two different polymer solutions that are mixing very nicely, and many different options. It usually means that you have a second phase, at least when you're spinning it, because those two phases then don't want to mix. This can be either even a core shell structure, it can be relatively elongated, but it can also be relatively finely dispersed. When we're saying that it's forming two phases, that can already happen in solution. In this case, it would actually go into emulsion electrospinning territory. And of course, the advantages of this that we can influence basically everything from exactly the solution that we're making. We are adding the specific components that we need and to achieve either structure or composition exactly what we want. It's in one step, so there's no further post-processing unless you need it to. There's a mixture of properties that usually comes out. So if you have a nice blend, it's a mixture of both polymers if they're mixing nicely, but it can also be that you have a sacrificial component that you can basically resolve afterwards to get some more interesting architecture or anything that needs to be released afterwards. Issues, of course, are that you can influence your whole spinning behavior like this, which might go against what you are used to on your machines. It's not necessarily easily removable. Imagine there's a proper blend, then the inner compartments are not actually easily accessible. And as I said, it might actually form an emulsion instead, which complicates the electrospinning, especially on a nanospider somewhat, but not necessarily if the emulsion is relatively stable. For emulsions electrospinning directly, there are different ways, for example, with oil and water or water and oil options. There's a nice example where they used PVA and corn oil to encapsulate that inside. You can use emulsifiers, you don't have to. There's different options to play around with droplet size and humidity, which effect that then has on the electrospinning. The good thing is it basically replaces to some extent coaxial electrospinning in needle electrospinning. So with needleless, you can do this all in one go without coaxial electrospinning, but of course you don't have that nice control over it. So whereas you get with coaxial nice core sheath structures, you might not get that with needleless electrospinning. And of course, you can use it for reactive electrospinning. What we've used this blend for, we can also use particles or emulsions directly that we can solidify before or after. And we've incorporated, for example, in a completely PLA composite, everything based on PLA, nice fragrance release over time. So still after a year after manufacturing, there's still a nice odor of hibiscus. And we have a certain thermoresponsiveness so that when we heat it up, it suddenly smells like mint, which is very nice for some, let's say, textile applications, but more importantly, also for biomedical applications, because this can easily be replaced by certain drugs. As I mentioned, capsules, we can, of course, also make this whole dispersion electrospinning. The last presentation gave some nice ideas of how nanoparticles especially can be used in needleless electrospinning. But with needleless electrospinning, we're actually in the fortunate position to also use microparticles. And we have a large range of sizes that you can use here. And that means also particles can be biological particles. It can be solid substances like drugs. It can be minerals. It can be capsules. It can be anything really. And for this, admittedly, we still use the old setup with the multi-wire version because there is absolutely no limit on particle size, except for, of course, it might not fly very well. And also it might separate out over time, but because we have this consistent mixing, is still a very good opportunity for us. But what you can see down here, we've done everything with the standard wire electrode. So you can use relatively small microparticles, which are in this case capsules, even though it looks like beads, but it's actually capsules. And we can also use microparticles. So this one would be completely encapsulated. So you can see here a nice layer of polymer on top of it, but you can also have something like wrapped around it. So that's very nice. And we are looking at publishing something like this in hopefully this year.
Mm-hmm.
So as a last overview, applications range from air permeability, gas and vapor permeability, biocompatibility, as cells really like this as a substrate, but aren't really growing through. So you're not having any issues with tissue ripping off when you remove it, or at least not much. Repellency and filtration, as we've seen here in the nice Hello Mask project from my colleague, where we've made a transparent mask. And this is basically all the primary membrane properties, but we also have secondary membrane properties that we can especially incorporate with blend or dispersion or emulsion electrospinning, or simply with green solvents. A bit more sophisticated thinking, we can get sustainability, biodegradability, which is what the whole idea behind this is. But we can also have specific functionalities. We can have release of volatiles. We can have functional activation. So in this case, we've made a photoresponsive capsule into the barrier membrane, into electrospun membrane. And this basically gives us a photochromic effect. So we irradiate it with UV light, and then it returns once the UV light is turned off. This can be used on one hand again for textiles. For example, there's strong sunlight, you have a change in color. It can be used for curtains, but you can also use it for capsule release. So there are certain capsules that we can include that release upon light. And this can be enzymes, it can be drugs, it can be many different things. Of course, you can change all sorts of different properties, color, physics, chemistry, anything basically. So I hope this gave you a bit of an idea of what the applications could be. So with that, I basically just want to refer you, if you have any more questions, to us. That's the Biomimetic Membranes and Textiles group at Empa St. Gallen. We are open to industry collaborations, we're open to academic collaborations, and we are also coming soon on booths and presentations in PPS 38 and ITMA 2023, if you want to have a step by there. But apart from that, you can find us on the internet and simply get in contact, and we're always happy to collaborate on anything, or even just for some expertise or different perspective. Good, well then, thank you very much for your attention, and any questions, I'm happy to answer them.
Very good. Thank you, Gordon.
I would say, wow, so many options here.
Yeah. I mean, we understand this is a very, as we mentioned before the start of the talk, how important this subject is, and how much, of course, the momentum's gaining towards sustainable and green. You know, we have people come to us, our customers come to us and say, we want it to be water soluble, it needs to be breathable, it needs to be hydrophobic and oleophobic. So it's you know, that's a challenge that's coming quite fast. And speaking of that, talking about the PTFE dispersions, you know, we talk about some companies have said, okay, PTFE is safe because in general, PTFE itself in the final form is somewhat safe because it's very stable in the environment. But there's other aspects of the production of PTFE and the dispersions related to PFOAs, which are, you know, come up all the time. So can you make any comments about PFOAs?
Sure, exactly. So PFOAs are definitely a high health concern. But it's important to know where they are coming from. So, of course, without PFOAs, you don't have PTFE. It's simple as that. But there are certain applications where you simply need PTFE. I already mentioned, especially if you want to use your membranes in the environment, basically every polymer will degrade over time due to UV, due to oxidation, heat, whatever there is. PTFE, not so much, because it's simply very inert. The only way you get it to degrade mostly is by heat. And of course, that's why it's a bit of a concern in pans, but considering the degradation temperature of about 400 degrees, it's not necessarily an issue. Usually you don't go that high. But yeah, with electrospinning, you definitely have the option to use, they say PTFA emulsions, but more accurate would be PTFE dispersions. So that means you're having small PTFE beads in a water solution or dispersion. The problem there is often they're using, it's not actually clear what sort of emulsifiers they're using there. So to keep this suspension stable. And there it could well be that there are more PFOAs used. So in this case, it would be better to go back to PTFE particles and use them in a solution directly with a, let's say, soluble polymer, and then suspend them in there without any further additives. And that's what we're also working on. It is definitely possible. We're just trying to make that a bit more approachable. But yes, that's, for example, we are using a DMF soluble polymer, and we can simply disperse the PTFE particles in there, and we can get reasonable fibers out of it.
So when you're talking about the PTFE particles, what size of particles can you make in this with the dispersion not available from the company, from the producer itself? Sounds like you're taking them and grinding them or something like that after.
No, not necessarily, because with this grinding process, again, there's a problem of friction. In the worst case, you're getting some heating and maybe some issues after all. Theoretically, there's also the option when you actually destroy these particles, there could still be some PFOA inside, even though it's highly unlikely. So it's better to just keep them as they are. And in this case, you would simply go with whatever you can get, basically. So we've used in the order of 100 nanometers to 1 micrometer and above. The limit is basically just the electrospinning method that you're using there. And of course, you have to somehow disperse this. For this, again, high viscosity solutions are usually better to keep it more stable, to keep it floating for longer. Makes the mixing a bit more difficult, but with a standard overhead stirrer, it's also not a problem. So yeah, there's basically no limits that you can use. And the best thing is you don't necessarily have to only use PTFE for this method. You can use even PET or other very hardly dissoluble polymers that you can also use as capsules, and you get these nice beaded structures out of it. And you can also flatten them a bit depending on how you're treating them. With heat processing, you fuse these fibers together, basically. Where was it?
And so in these cases, you're using like combination of non-fluorinated surfactants and other polymer carriers, or?
For putting them into the organic solution, you don't need any emulsifiers whatsoever, any suspending additives. You can simply add it in there, and simply by the viscosity and by the fact that you have a relatively viscous polymer solution with DMF, you have both the hydrophilicity and hydrophobicity at once, which let's say encapsulates or let's say forms a film around the particles much better. So they don't crush out of solution in the time that we are spinning them at all.
Very cool. Go ahead.
Yeah, I got the message from a director here. So please use the Q&A section for questions if you have. So not use a chat or anything, but this section that you can open up on the toolbar on the bottom of the Zoom application, right? And we have now one question here. I read it.
Yeah, go ahead.
So there's a question about the cost, which is associated with most of the green solvents. So how can the challenges with the scale up be tackled, especially when you factor in the large volume of electrospin materials? So how do you handle the cost of the green solvents? That's basically the question.
Yeah. Relatively simple. There are two options. Either you go with the very easy to use solvents, for example, as I mentioned before, PVDF HFP as a relatively high quality polymer you can dissolve in DMF, but also in DMSO acetone mixtures. The acetone is relatively small amount in there. You can also achieve similar stuff with ethyl acetate as a co-solvent. They increase the solubility a lot, but they are small enough in amounts that they are not a risk of getting into combustible limits. So they're still safe to use, but you have to invest something. For example, if you want to go completely pure with these green solvents, or let's say something that's easier removable like ethanol, then you have to invest a bit into making your whole process less flammable. So for example, as I said, you can include some nitrogen gas stream in there. Another option is, of course, you simply try these solvents, because the more demand there is, the more cheaper they will get at some point, because they have to produce more. Also with all these regulations, there simply isn't much of an alternative at some point. DMF will get more cranked down on, so you have to switch at some point. And as I said, there are some options in the, let's say, less published method until now, which includes the ketones, esters, esters, amides, and natural compounds, which are not necessarily advertised too much by BASF because they're not aware of it. There are some that we're working with that are really quite cheap, and we can dissolve a whole range of polymers in them, which I was surprised in initially. So basically working with academic partners who can play around a bit to find out these nice mixtures. That's the trick there. And of course, keep in mind that the standard BASF versions that are advertised as methyl, THF, and styrene they are not actually ideal for electrospinning because, as I said, solvation issues, they are flammable still often. So I can't really recommend them specifically, but rather the more obscure ones that you probably wouldn't notice straight away. But of course, there's always the option browsing the big catalog of potential solvents and then finding the right one. That's basically what we are doing, but with a bit more chemistry backed knowledge and with a bit more opportunity to play around with our just as low as 8 milliliter.
Okay, thank you.
So related to solvents, before we leave that topic, do you guys use any software? I know you said you choose some solvents. I think maybe to talk about how you choose this, maybe a little bit of a methodology of how you might choose a green solvent alternative.
Yes.
And then is there any software, anything that you use for that, or?
Definitely. So the standard software, I actually forgot the name. I'm pretty sure you actually want to know a specific software that you probably also used. The Hansen solubility parameter software mostly. That's a good starting point, but it's not from experience the best version. So for example, you still need to, if you actually want to get some useful results out of software, you actually have to type in or select the solvents that you are interested in. So that means you're already giving a sort of a pre-selection. That means you already have some sort of familiarity with the solvent. So that means you basically need a chemist on board that already has some experience. But Hansen solubility parameters is definitely a good version to start with. Problem is, it doesn't tell you anything of how well soluble it is. So often we found out that the solubility for electrospinning is too narrow. So for example, after adding, I don't know, 5 weight%, for example, it already crushed out of solution. And that means it might actually form colloids or whatever there is. It's not ideal for electrospinning. Doesn't mean it doesn't work necessarily, but probably for industrial applications, it's not suitable because it's not scalable. So again, better switch to something that you have experience with or that's already mentioned in academia to work. And again, that's what we are working on, to be some sort of advisor that can help with this selection process.
Okay, thanks. There is another question coming. So can you speak more on the heat treatment versus microstructure on the particle composite fibers? Also, how does this affect properties and fiber shedding?
Yes, so of course, always when you have higher temperature, there's a risk of oxidizing something. But in the case of, I think it was up here. Yes, in the case of the PTFE particles, they are very stable. So the idea is to choose a temperature where the polymer particle that you're using is still stable and starts melting, but not yet oxidizing. You're doing this whole thing under nitrogen atmosphere, ideally, so that it doesn't have a chance to oxidize in the first place. And that means it probably won't rip apart, as you mentioned. Yeah, then you have to adjust the temperature, and you're using a sacrificial polymer on the outside. In this case, they often use PEO or PVA, which simply gets burned off. So while it's burning off, it's still providing some sort of structure, to some sort of integrity, like a scaffold around it. And that's why this looks like this after heat treatment. So this is roughly 350 degrees, just above the melting temperature of PTFE. And there's loads of studies on which temperature exactly to use. What we are working on is a polymer that actually melts higher than this. And then you have the option to theoretically form very nice smooth structures, but yeah, it's not as simple at the moment.
So someone's asking a slightly different question, but more about the conditions in the spinning chamber itself. They wanted you to comment on how does humidity play into morphology and the spinning process?
Sure, that's known. I mean, it depends on what sort of mixture you have. Something very interesting that we've been working on previously, but not using green solvents whatsoever, was these very porous particles here. So in this case, the more humidity you have, the more phase separation you have, and that's where you can get these structures. But again, in this case, often you have to go via chlorinated solvent, so that's not very great. What you get instead is the more you increase the humidity, the more, let's say, bumps and wrinkly structure you get. So not quite as much as here, that was post-processed, but it can look relatively rough. The problem with that is if you increase the humidity too much, you simply get your solution to crush out directly on the wire. So that's not helping your spinning at all. So there are certain limits. You simply can't get higher humidity, which is a particular problem with our setup, actually, because in winters now we have relatively dry atmosphere, so we can spin all these non-humidity requiring relatively nicely. And then in summer, when it gets so warm, we might not get below 20% or something humidity, and that means we already have some of these artifacts in there.
definitely. Next one. So there's a question about how about the combination of 2 or 3 polymers for a sustainable electrospinning process? And it's following as one of the polymer is not fitting to formulation of drug delivery. So I mean that the person mean that if he's for a medical application, and then, and then if one of the polymer doesn't fit actually to the medical, let's say,
Sure.
composition, how to handle that?
I mean, fitting is a bit of a question. As I said earlier, biomaterials, you can basically call all of them biomaterials. They, as long as it doesn't attack the host or cause any strong inflammation, it should be fine. In fact, PLA is one of these issues. If you leave it too long in the wound, it will cause inflammation. That's why it's been used as hernia meshes and then actually found to have massive problems with the body repelling it. That doesn't mean, so for these operation problems, it's easier to just remove it after a certain time. With electrospun membranes, you don't need to worry about it too much because simply there's not enough material. It degrades so quickly and the body gets rid of it relatively quickly that it shouldn't be a problem. You can theoretically also, if you use a patch, for example, external, use something that's way more stable, for example, PVDF HFP or something like this, as a matrix, and then you mix another polymer inside. Problem is with this, so let's say PVDF HFP would certainly repel the drug, and then you have another polymer in there that can, let's say, absorb the drug or maybe encapsulate it better. The problem with that, you don't know what's going to happen until you actually try it. So that's a bit of an academic problem in it. You can't 100% know what's going to happen. There will be some that actually are still staying in this sort of shape where you have these compartments inside. That would be ideal probably for drug release. As long as there is some sort of connection to the surface at some point. The other option is that you're actually getting a phase separation to some sort that might still be acceptable, but in the worst case, they are separating directly while spinning and you're simply getting 2 separate polymers. That can also happen. In this case, you would, if you're lucky, have some sort of coating maybe where there's the drug incorporated to provide some extra stability to it. But in the end, you have to test it.
Mm-hmm.
And then we have one more question about sort of the spinning environment. Somebody was mentioning the nitrogen gas was quite interesting to put, you're talking about putting a small amount of nitrogen to sort of make the chamber not so explosive. Can you make more comments about how much and then maybe what types of polymers you've done that with?
Sure. I mean, it depends entirely on exactly what solvent you're using because there are different flash points. The flash point is always measured. I don't know if you've ever seen these flash cup tests directly on an open cup where the solvent is basically evaporating directly from the cup and then there's a flame going over it to try to ignite it. We don't really have that situation in the nanospider because we have this little wire that basically completely dries up, or maybe not depending on how quickly your ship runs over it. And you don't have enough material that you can actually have a proper explosion or flammability risk. Yes, you can have sparks or something like this, but simply if it's so dilute and that constantly the airflow gets rid of it, the risk is minimal to non-existent. The issue, of course, is we have 21% oxygen in the atmosphere. The lower we go with this, let's say 15% oxygen, the flash point is increased dramatically. So there's simply no risk anymore. The flash point goes maybe from, I don't know, something like 25 degrees, sometimes in some organic solvents, goes probably up above 40, 50 degrees. So it's simply not an issue anymore if you take away the oxygen. And yeah, so what we've tested it specifically, we didn't actually need to test it because we are using ethyl acetate as well, acetic acid, and all sorts of polymers that technically do have this issue, but because we're using the small scale, we can experiment with it. It's not that much of a concern to us. And we've also implemented a solvent concentration detection, and the concentrations you reach in the air are they don't show up on the concentration measurement. So it's completely irrelevant. With high enough airflow, so usually we go then with max or close to max, you don't change much of the membrane structure, but you're getting rid of basically all the solvent that has the tiniest of risk at all to form any sort of combustible mixture, and it simply then doesn't.
Yes, there was one question about if somebody was wanting you to make some more comments about bioresorbable polymers and what might be good solvents for those, and typical solvents for those like PCl, PLGA, those types of polymers.
Yes. I mean, PLGA, again, if we're talking about costs, then PLGA is not a problem because that is already super expensive. So you might as well go very deep into the solvent repertoire that BASF or whoever has. They might actually be best to recommend you something there, even though I'm not sure they actually have electrospinning specialists. But in general, so what is often used is acetic acid, which is still quite friendly. I mean, it's basically vinegar. The problem is that if you dissolve it, especially also PCl, if you dissolve PCl in acetic acid for a while, so let's say if you have a batch that you're going to use at some point later after months or something, you're definitely degrading your polymer directly in the solution as well. That can in fact sometimes help because, for example, you actually want a more beaded structure. This would actually help you achieve that by simply letting it mature, so to say. But generally you have issues there. Another option is what's mostly used as alternative to DMF is simply DMSO acetone or DMSO ethyl acetate. Those are some very good options. And as I said, we are working with other of these specific solvents that are more obscure, but also used from biosources. As I said, furfural is a very nice starting point, not it itself, but whatever components get made out of it to look into. So yeah, we got a solution of above some PLA grades, we got above 30% solubility in this solvent. So there are some very nice options out there. You just need the experience or ideas from academia.
There was one very interesting polymer you talked about, PETG, which is very, very difficult to dissolve. Can you discuss that a little bit more?
Yes, again, we've used our special solvent. Again, it's not that special. If you know which one it is, you can easily source it everywhere. But we actually managed to spin PETG itself, and we got some structures out of it just in an initial test last week that are even superior to ePTFE. So ePTFE is this drawn, let's Gore-Tex membrane. And look, if you're looking at the scale by here, 1 micrometer, we're having nanofibers here that are tens of nanometers at the most, and that's very impressive. Of course, it's a bit difficult because again, you have to get this dissolved and stay dissolved and everything. It's not that easy. If you look in literature, there's often a bit of heat, so that's also what we've used in this case. But as long as you keep it moderate, you can actually spin with this, as we've shown here. So it is entirely possible, and that's what we're working on also in the future to make this even more approachable. And again, we have not nearly looked into all of the interesting solvents. We are, for example, having collaboration with ETH or EPFL, sorry, with some lignocellulose parts. There's, for example, DXF as a solvent, but again, this is supposed to replace DMSO at some point, but problem there is it's not actually liquid at room temperature unless you use a co-solvent in this case. So there are many very interesting, let's say, new solvents from nature that haven't been used in electrospinning yet, and that's what we're trying to change.
Very good. I feel like we had a lot of questions about solvents. So I think that's a very hot topic for everybody since, of course, the process is quite solvent intensive.
Exactly.
You know, I think that we're kind of winding down here. The rest of the questions, I believe, are more about just the questions that are general questions that are, some of them are for us, Elmarco, as well. So we definitely will solve those and send you the responses. Also, this presentation will be shared. So there was a question about whether the presentation will be shared, and that will be shared. I'd like to thank you, Dr. Gordon Herwig, for coming on and talking about this very important issue with us.
Thank you.
And everybody that attended. So I think that'll be it.
Yeah, and then please visit our very fresh website, actually, that we launched just last Friday. And then you can contact us through the contacts that you found there, which, yeah, I think it's very useful. And we are here to answer all your questions.
And be on the lookout for February and March. We'll have 2 more web series that are coming along as well. So with that, I'd like to say thank you again, and we'll see you next time.
Yep.